Okay, so let's review what we did last week. We looked at a lot of tricky computations just to illustrate what can happen to limits and how they work and how they help us to understand certain things, and that is including things such as division by zero. Okay, division by zero, adding infinities, subtracting infinities. Some of these ideas can be worked out, and some of them we did. And this is a good example of when you have to do it algebraically in order to understand what that thing is. N squared plus 1 or n squared minus 1. So division by the highest power, that's roughly what it's called. We just in a minute will go there again. And because it's worth trying to generalize these ideas of whatever happens to things at infinity. So this is what I had in mind. We'll get to this back in a minute. But right now, what I have in mind is this. So limits of polynomials. So that's another theorem. The theorem, well, first of all, what a polynomial is. So n squared plus 1, n squared minus 1, it is just another polynomial. It just happens to be one of the simplest one, is a quadratic polynomial. Okay, then if we have a cube, then it is a cubic and so on. And we want to take care of all the polynomials at once, so we wouldn't have to worry about them. So a polynomial looks like this. So the power starts at the highest, so assuming that this is not 0 and the AP is not equal to 0, the leading coefficient that's what it's called, and in other words, it is the coefficient of the highest term in the whole expression. Okay, so as you can see, the powers go from p and down. So p is the highest power, and then at the bottom you have a 2n squared, a 1n, and a naught. Okay, that's my polynomial f of n. Okay, so we're going to study polynomials as functions as well, but for the time being, we just want to know what's happening if n goes to infinity. And the lesson is, I hope we have learned, is that only the leading term matters. So that's the informal way to put it. Only the leading term matters. Only the leading term and the leading coefficient at infinity. So you know about polynomials. They have all go up and down, cross the x-intercepts. You can factor them. They have minimum, maximum points, all kinds of weird behaviors. But at infinity, which is what we have been talking about, the pattern is very clear. The leading term overpowers the rest of the terms eventually, and it determines the behavior at infinity. So how we put it, it's very, very simple. So the limit of f of n is either plus infinity or minus infinity. So if the leading term is positive, you have positive infinity, otherwise it's negative infinity. That's the whole thing. Okay. So in other words, these are the parts of the graph that we only care about. Long-term behavior, which is what sequences are all about. What happens to the long-term behavior? In fact, let me correct myself. This does not apply. Only the one on the right, because these are the n's. These are the n's, And we want to know either it goes to positive infinity or it goes to negative infinity, something like this. So this is the negative infinity behavior, and this is the positive infinity behavior. Okay, so yeah.
Does that mean that all polynomials like diverge?
That's right. Yeah, that's right. Yeah. But then the next theorem is about rational functions, which are fractions of polynomials, and then those have much more in stock for us to worry about, which is that example once again n squared over n squared minus 1, n squared plus 1 over n squared minus 1 indicates. So even though it is made of two polynomials, the behavior the behavior of the numerator and denominator, as you can see at the bottom, is infinite. Okay. However, the whole thing turns out the answer is 1. Okay. So that's not unusual to happen to rational functions. If you look at the whole thing, that's a rational function. So why such a nice behavior in the convergence? It converges because the powers, or the degrees rather, of the polynomials are the same. So the numerator has quadratic polynomial, denominator is also quadratic polynomial. So that is why they are comparable, and that is why the limit exists. Okay, but in general it's not the case. Let me write up the theorem. So limits of rational functions. So this time we have literally two polynomials. Unlike in the last theorem, we have two polynomials. So we have a p not equal to 0, bq not equal to 0. So the degree might not match. And then I have two polynomials. Let's say, well, let me just write out the polynomial, the rational function. So it's a fraction. The numerator is exactly the same as the one I wrote up there. And the second one, the denominator starts with bq, so it does not have to be the same degree. But as you can see, the pattern is the same. So some of these might be equal to 0, except the very first two, the first term is not 0. b2n squared, b1n, and b naught. Okay, so that's a big fraction, just like that example. And then there are three possibilities. The infinity is still a possibility. So okay, so that's given. Then the limit fn as n goes to infinity, there are three possibilities. First of all, it could be still infinite, just like in the previous example. All is determined by the leading terms. So if I have here my explanation is only the leading term matters, all I have to change is that the singular to plural. Okay, so that is my explanation. Only the leading terms matter, and the reason is the same. So powers for each polynomial, the only the leading term matters, and then at the end we have two leading terms to worry about right here. Okay, the two leading terms, and then they, it's like I don't know, two qualifying tournaments and two winners at the end that meet at the final. Okay, so that's what's happening. So this is bigger than the rest of them. This one in the numerator. And the other one in the order BQ and Q is the one the strongest in the denominator. So at the end we have to compare them. Okay, so once again, whose power is bigger wins. And you can tell if P is larger than Q, what's the answer? What's the limit? The numerator is way stronger than the denominator. It goes to infinity. Okay. Let me put plus or minus infinity depending on the sign again. And on the other hand, in the opposite situation, p is less than q.
Goes towards
0,
zero.
right? So that it's being dragged by the denominator. It overpowers the numerator and drags everything towards 0. And then, well, then there is the third case, and that's p equal to q. And then what do we do? Well, you can imagine once again that all of the rest of the terms in the numerator and denominator have gone. In fact, that's probably the easiest way to think about the whole thing. It is as if the rest of the terms just disappeared, and whatever I have circled over there is the only thing that's left. So AP and P, BQ and Q. Okay, so in the last case, the one that is in the middle actually, P is equal to Q, so we are left with what? P is equal to Q, so these are gone. And we're left with nothing but the leading coefficients. A, P, B, Q. And that's the answer. So it is a number. Just like in that example from last time, it is the leading term was 1 in the numerator, in the denominator also 1, so the answer is 1. So AP, well, let me just write AP over BP. Because P is equal to Q, I could just as well have 1. So let me just illustrate this quickly with a couple of, with 3 examples. So case number 1, I have, say, an squared divided by a 1000 n plus 1. Okay, so as you can see, the denominator starts strong with a whole 1000. And numerator is 1, but it doesn't matter because eventually n squared overpowers it, and the whole thing still goes to infinity. Okay, so it starts small, but then it ends up with infinity anyway. Okay, number two is the example we just had, but so n squared. Let's have just for a change n cubed. That doesn't matter. Once again, I'm making sure that 3. How about this way? Okay, 3n cubed plus n plus 4 divided by 2n cubed minus n squared plus 3, and I'm adding up terms without thinking because those terms don't matter. If we're talking about the limit, n goes to infinity, only the leading term matters. Leading terms matter. Okay. So, well, there you go. We have left with 3 halves. Okay, and similarly for case number 1, case number 3, you just turn it upside down and you are in pretty much the same place. So it has, say, n squared plus 1 million divided by n cubed plus 1. Okay, so, well, there you go. You will end up with 0 because n cubed will overcome eventually n squared. So this is how we handle infinities. So even though both numerator and denominator are poorly behaved, they can be might be able to cancel each other, and the end result of the whole fraction might be something predictable, manageable as just a limit. Okay. So the proof, by the way, is you can guess how I arrived to this conclusion. I do what I did with this example. I divide by n squared. See at the bottom, I divide by n squared. I divide by n squared, and that created the situation when neither numerator or denominator goes to infinity. Okay, so that's why I was able to apply the quotient rule. So same thing works here. Once again, if I divide by the highest power, which is, say, p, then I will end up in the numerator, and I will be left with AP and nothing else. Okay, And denominator will go to 0, so the whole thing is infinity. So the proof is takes just some time to learn if you want to. So that's why I encourage you to, if you want to use it in the future, and not trying to remember formulas. So at the end, this theorem is ultimately, this is a formula to be remembered somehow. Eventually you'll have to remember this formula, but on the other hand, it is much easier to remember this part because it's short and it's kind of intuitive. So the leading coefficients at infinity, only the leading terms matter for polynomials. Okay, so well, there you go. And then you derive almost instantly in this manner over here, derive the conclusion of the theorem. So once again, the punchline is the formula over here, while the build-up is this. So this is the build-up. Okay. So so that's not the rest of this. So all kinds of fractions and strengths of functions can be compared, and we'll do some of that in the future, because polynomials are only one thing. They're exponential functions, and exponential functions are yet stronger than any polynomial of any degree, so we'll have to address that at some point. But this is a good start. This is a good start, and then there are certainly other things. So another issue that we have looked at was where is it? How to deal with the algebra of infinities, as well as the division by 0. I'm wondering where it is. Here it is. Okay, so that's, once again, this is not the whole thing. You want to have four rules plus the rule of plus the negative infinities. There are more algebraic operations. So, for example, I could ask myself, what is 0 to infinite power? Or rather, what I meant is to say is, what is 1 to infinite power? Okay, so it is just as it might be a problem as the rest of them. So just, it might make sense or might not make sense, but we have only these, and just limit ourselves to some short list, because at some point you're really not getting anything. It becomes more complicated, even though somebody might try to confuse you and try to challenge you with a problem like that. Remember always the idea behind of operations are like that. When there's algebra is not the one that you learn in middle school. It is algebra with numbers. It means that there are sequences involved. So what is the meaning of 1 to infinite power? It means that one sequence converges to 1, the other diverges to infinity, and you take an exponent of it, and then you ask yourself, what's the limit of the whole thing? If you can sort it out, then that's good. But just the plan is that's the only way to address, really, rather than trying to guess what it is. And you can see the conflict, right? 1 taken to any power should be 1. On the other hand, if you take any number which is not 1 to infinite power, it will be infinite unless it is 0, depending on whether it's larger or less than 1. So there is a conflict there. So it's ambiguous, just like dividing infinities. Okay, so infinity divided by infinity looks like 1, but why not 0? Why not another infinity? So we already have seen that the cases when this could be any expression. If you can find appropriate sequences that indicate that the meaning is the expression is meaningless. Okay, so those two in the upper corner are meaningless. They're called the indeterminate expressions, and you remember the plan is to go into algebra to resolve it. Okay, so right now I want to and so, like I said, I just don't want to go into that too deep, because you will just get lost in it, and there are just more important things to do. Right now I'm going to review a few important theorems about sequences as quickly as I can. So one is a truncation of sequences. All of them are very predictable. It's better to be stated. So you can freely use it. So when it's stated, you can refer to it and you can really use it rather than try to rely on your intuition. Truncation meaning you cut off part of the sequence, the beginning of the sequence. So say, so if you have my sequence, and let me remember that we always have abbreviated sequences, but sometimes it actually matters where it starts to make a point. Okay, so the sequence is written like this. So this time I'm not starting with n equal 1, I'm starting with n equal p, and then from p I'm going on to the right, and if the sequence converges, then any sequence with a larger one, say, I will throw out the very first element of the sequence. So I'll start with p plus 1. That's truncation. And the conclusion is the same. Same for divergence. Okay, so sequence converges to a certain number. You throw out the first element of the sequence. It's pretty much the same sequence. It still converges to the same number. If the original sequence diverges, then the truncated sequence also diverges. Okay? It is just a matter of convenience. Now here's another one. So one of the here it is. One of the you can compare sequences as inequalities like this. Okay, so one is larger than the other, and then we want to if we know about convergence of one of the sequence, what sequences, what can we say about the convergence of the other? Okay, so so we assume this, and now number one, if both converge, then limit an is larger than or equal to limit bn. Okay? Something very predictable. I mean, you can illustrate it in addition to what we have done. So if this is one sequence and it converges to A, so this is an, and bn is smaller, always below it, like this, in some way. So then if it also converges, it converges to a number that is less than or equal to A. Okay, so we do not, however, so once again, be careful about using the implied, be careful about implying about the conditions. There is no, or the conclusions, there is no conclusion about convergence. So it is assumed that they converge. Then we have an inequality about their limits. If so, convergence means limits exist, so we can speak of A and B, but if they diverge, then we're not saying anything. So you have to verify the condition first, and then before you apply the punchline. So this is the punchline. Once again, the condition is on left. You verify the condition, there are two of them, and then you can conclude something about their limits. But if there are no limits, there is nothing to compare. Unless we're talking about infinities. So infinities can also be useful. So for example, limit an is equal to negative infinity, then so is the limit of bn. So once again, if one sequence dominates the other in this manner, then there is no way bn is going to end up anywhere else. It's always, the trend is going towards negative infinity like this, then bn being below an will end up in the same place. On the other hand, if bn goes to positive infinity, then an goes to positive infinity too. Okay, so a very convenient conclusion. But once again, this is my hypothesis. These are my hypotheses, and the conclusions are these. So this one is the conclusion. That is the conclusion. Okay, so watch out. Watch out. There's a here actually you do see a conclusion about convergence or rather about divergence. So it is you don't assume any particular kind of convergence as in part 1. But still, you have to verify the condition. So just the inequality the one that we started with is not enough to draw just about any conclusion about the new sequence. How can we, under what circumstances can we make a conclusion? And the answer is when we squeeze two sequences between two convergent sequences. So roughly it is like if this is one sequence and this is the other. So as you can see, they converge. At least that's what I'm trying to illustrate here. And then you can imagine that there is the third sequence that behaves wildly, running between these two. So these are two convergent sequences known to be convergent. And then the third one runs around maybe in some weird way like this. Okay? So say this is a Cn. An is the smallest, An is the smallest, Bn is the largest, and this is the inequality. So I have inequality Cn squeezed between An and Bn. Okay, and then we also, and we want to conclude. If you look at the picture, you can probably guess that what our conclusion is. Look at it, how An is getting closer to Bn. Okay, why? Because they both converge to the same number. So that's the assumption. Say 2a. Okay, An and Bn converge to the same number, and which means that they're getting closer and closer to each other, which means that there's less and less room for Cn to run around. Okay, so then we conclude based on that. So once again, the key assumption is that the limits are the same. We conclude that Cn also converges. Okay, so then Cn converges to A2. Okay. The standard example to illustrate why this matters, you can choose Cn equal to 1 over n sine n. If you remember sine n, what the sequence looks like, it looks like, you remember the random kind of sequence? Okay, just about almost like this. Running around almost random manner between -1 and 1, okay, -1 and 1, okay, but that's sine n. But once you multiply by 1 over n, the amplitude, the swing, starts to diminish, and that creates a squeeze. Okay, so this is what it's going to look like. I'll put the sequence of, this is what I plotted here is sine n, and now suppose we have a sequence like this. Bn is equal to 1 over n, so positive numbers, okay, positive number reciprocals going towards 0. From the bottom, we're squeezing it to like this, and these are An is equal to -1 over n. And then in between, the Cn is here. This is Cn running around between. It's still very wild, but it cannot be wilder than the distance between the two sequences, and it diminishes. Okay, and so we conclude, as the theorem says, we conclude that there is convergence. Okay, so the standard name is the squeeze theorem. Another one is the sandwich theorem. And it's called the two policeman theorem. Okay, so it's a popular theorem because it proves convergence, which is sometimes hard. So once again, while behavior of the way I explained to myself the meaning of why it's called sandwich theorem, it is you're holding a sandwich. Okay, well, the sandwich, two buns, and then in between the two buns, all kinds of business is going on. So there is bacon, there is lettuce and sauce and all that. You can't really touch it, but you want to eat it. So how do you make sure that you eat what's in between, the good stuff? You make sure that the two buns go into your mouth. Okay, that will guarantee, according to the theorem, that you will eat the whole sandwich. Okay, at least that's best I can do. You want sometimes have some explanation of the mathematics, and that somebody came up with the names. You can only guess what it means. The theorem about two policemen, how you interpret it. So those are, I suppose, two policemen. So we will revisit this and a lot more what we have seen just recently when we switch soon to functions. Okay, so this has been limits of sequences. Now we're going to look at limits of functions. But first, a couple of more theorems. Here's one. Unimportant theorem. Monotone convergence. So AN is increasing or decreasing. In other words, AN is less than or equal to AN plus 1. That's increasing, right? So we progress higher and higher, or decreasing AN larger than or equal to AN plus 1. So we're going down. Okay? So most of the sequences, as you have seen, they are neither. So that sometimes they behave wildly, such as sine 1 away. Okay? So that's the condition. Condition number 1. The second condition, AN is bounded. Okay, in other words, AN less than or equal to, remember, absolute value less than or equal to some number Q, which is the bound. Okay, the bound. So the bound of the sequence from both below and above. So in other words, we want to guarantee that it's not running away on one hand. On the other hand, it also behaves in a very regular way. So it is increasing. So imagine that the sequence is increasing, but it's not allowed to run away into infinity. So this one runs away to infinity. Okay, this one goes to infinity. But suppose there's a bound. So there's a bound, and you cannot go above it. Then your behavior has to be like this. So you're still increasing, but you have to slow down inevitably, because otherwise you will run into the bound, and you are not allowed to. Okay. So and then the conclusion is that AN converges. Remember, I did mention the flip side of this theorem, or maybe this is the flip side of the other theorem, is then convergence implies boundedness. So convergent, bounded. You cannot reverse. Many statements in the theorem can be reversed. So even the Pythagorean theorem can be reversed. You know, remember the Pythagorean theorem says that if you have a right triangle with sides ABC and C is the side opposite to the right angle, you can, and then the conclusion is that A squared plus B squared is equal to C squared. You can reverse it. You start with a triangle with and with the equation, okay, and then you conclude that the triangle is a right triangle. That's the reversal. There are a bunch of theorems like that, but sometimes it's not reversible. So that's, as you can see, this is what we talked about. Every convergent sequence is bounded, but not every bounded sequence is convergent. Right? Not every sequence, not every bounded sequence is convergent. And once again, example, all you have to do to disprove a theorem, hypothetical theorem, that you're hypothesizing about a theorem and you're not sure it's true or not. If you suspect that it's not true, then you don't have to prove the opposite. All you have to do is just give an example that shows that theorem fails. Okay, so an example when this conclusion that I crossed out fails. A sequence that is bounded but not convergent. Sine of n, that's right, sine n. So example proves or disproves the rule, if you like. A counterexample, the technical term is counterexample to a statement, and that's why you cross out the hypothetical theorem. So convergent means bounded, yes. Bounded means convergent, no. Okay, and that's why you have to add an extra condition in order to be able to conclude convergence. That's what this theorem is about. If you also add to boundedness, you also add monotonicity, increasing or decreasing, then you can conclude convergence. Okay, so the interaction between these concepts is somewhat complicated, as you can see. Okay, so let me take you back to this. Oh yeah, compositions. Okay, so what to do about compositions and of sequences with functions? That's what we're looking at. And this example is two examples reveal to us how we're going to use sequences to study functions. So ultimately, sequences are, at least in this course, sequences are used to study functions, period. So we're interested in the functions, and I don't have the graph of sine here, but so let me add. You already have the second example, the sine function versus the sine function. So as you can see, there's a confusion here. So the sine function in red looks like this, and we are concentrating on just one point on the graph. So this is y equals sine x. Okay, and the orange one is y equals sine x. Okay, so so the humor here, unfortunately. So I should have picked different function. But on the other hand, you can see how both of them are 0 at 0. Okay, sine of 0 is 0. Let's note that. Sine of 0 is equal to 0, no matter which one it is, or just in this one. Okay, so they also positive to the right of 0, both of them, negative to the left of 0, as far as we can see on the graph. Okay, so they're, in this sense, they're similar, but the fact that the second function is kind of flat on the left and right is really not the main difference. The main difference is the gap. The main difference that we want to pay attention to is the gap or gaps or jumps in the second function. In the first function, as you can see, there are no gaps. And specifically, when we're looking at 0, one point at a time, this way we're going to do it, one point at a time. So if we concentrate just on one point, so x equals 0 is our interest, and then we're looking at these two functions, and we can see that sine function remains continuous. Literally, the literal sense of the word continuous is that uninterrupted. There is something going on that in uninterrupted fashion, and there are no gaps, there are no jumps, and so on. There is no stoppage. On the other hand, very different behavior with the second function when there is a gap. There are two gaps, in fact, and there is a jump, two jumps. Okay, so and as you can see, we have discovered it how? By looking at sequences. So this is this one sequence we looked at, this one. We look at 1 over n, the point 1 over n going towards 0, and then see what's happening to. In other words, we are living, that sequence lives on the x-axis. It's here. This is my sequence. On the other hand, let me erase this maybe. On the other hand, let me take this color over here. This one is on the y-axis over here. Okay, so once again, the yellow one is a sequence 1 over n converging to 0 on the x-axis. Okay, so once again, this is the x-axis behavior, and I plotted on the right. Then we're looking at what's happening to y as x goes towards 0, and then we realize that the same thing happens. It also goes to 0. So look at it. So the yellow going left from right to left on the x-axis at the top. Okay, in the meantime, this blue one going down on the y-axis. Okay, so it is very similar behavior for both of them. Okay, and then we try to do the same on the with the second function. Okay, so once again, I take the yellow over here. Okay, I am over here on the x-axis, so that part is the same. We start with a sequence on the x-axis going towards 0, and then we're looking at what's happening to y's. Okay, so once again, I pick the blue one, and here it is, right below, right, this one. Sine 1 over n goes towards 1, so this is the not 0. This is where we are. This is the behavior of y. It is in fact constant. No matter what x is, as long as it's larger than 0, the value of y is 1, and so converges to 1, even though the value is 0. So that's where the gap comes from. Okay, so the limit behavior of y's, does not match the value of the function. Okay, so let me do that. State this again. So, so the limit behavior of y n is equal to f of xn. Oh, let's take 1 over n. 1 over n does not match. Does or does not match the value of the function at 0. Okay, so even though xn equal to 1 over n, it is going towards 0. Okay, and the y behavior has to match. Yn is equal to f of 1 over n. And then the question is, does it go towards f of 0? Okay, it might or might not. So let me make that picture again. So I'll actually look. Let's make up functions rather than sometimes specific functions might be or just more misleading. So let me plot the one case when there is a match. This is my function, y equal f of x. So once again, I have my xn's are here, going towards 0 like this. Okay, you see it? So we are on the x-axis, xn's going towards 0. Okay, now, but then each xn, 1 over n, has a matching yn. Okay, so this is how I find. So for each x, I will find the value on the y-axis. Okay, so each of them, and therefore there are two sequences automatically. So these are the sequences I'm referring to, are these. So we're studying now functions, which means that we are living on the xy plane, and there are x's and y's, and both of them might have sequences. Okay, so as you can see, I started, since x is an independent variable, I start with x, and then with the help of the function itself, I create a new sequence on y. Okay, so every point on the x-axis has a corresponding value on y, and which means that that's how we're getting a sequence like here. These are y's. This is the sequence, and these are y's. Sequence of x's produces a sequence of y's. So, like this. Produced by f. So that's what function is. It converts x into y's. And then we converted one sequence of x's into another sequence of y's, and then we'll see where it's going, and finally, and then the question is what's happening right here. Okay, so nothing. What's happening is what you'd expect it would happen. As you can see, the sequence on the x-axis going towards 0, the sequence on the y-axis going towards 0, as well as the graph itself going towards 0, and there is the meet at one single point, and everybody's happy. It means that there is no gap. No gap is what we discover. So we do this algebra over here, which is why we're doing this. We want to do algebra in order to discover or confirm the geometry on right. So how do we know that there is no gap? What if we zoom in? It seems it's not there. What if we zoom in? Maybe if we zoom in enough times, there will be a gap visible there. If you do it any kind of a graphic calculator, it might look continuous, or you do Excel. Every graph is made of dots. What if you go close enough and there is a gap somewhere? Okay, well, that's how you do it. You take a sequence of x's, converging all the way towards 0, and then produce a sequence of y's and see where it goes. Okay, so if there's a match, and the match is here, I put a question mark here in order to emphasize that it doesn't have to happen, and to demonstrate when it does not happen, well, the function has a gap. So let me carry this out, and I will make the function different only slightly, like this. Okay, and then it doesn't really matter what the value of the function is. So so the point is that this is what the graph looks like. So it's once again y equal f of x. Then I follow the same procedure. I have my x's here on the x-axis again. They will all produce y's, but you see the difference? These are the corresponding y's. Okay, so the value of the function might be anywhere else. It might be here, for example. It doesn't matter. The value, maybe there is, maybe the function isn't even defined. But as you can see, they do not meet together at the same spot. At the same spot, if the graph does not meet those two x and y's behaviors, as you can see in the top picture. Okay. So, and that is called continuity of a function. So this is a continuous, and this one is discontinuous. So continuity, discontinuity, you can guess the importance of this in the setting of signs, or that doesn't have to be signs. Certainly, if you think there's a gap is so small, maybe it's not important. Certainly, there's a possibility, but then you have to know what the accuracy acceptable for us to overcome that little difference, and it might be all right. But if you don't know ahead of time that how much accuracy you're going to need, what you end up with is a possibility of a catastrophic events. So it's like, imagine you're standing on a cliff like this, on the very end of the cliff. If it doesn't matter how small a step you make, you're gonna die. Okay, so that's discontinuity for you. It is a possibility of something catastrophic happening, no matter how small your error is. So you're supposed to stay here and not move, maybe move backwards. You're not supposed to go forward, but maybe you make a mistake, and if you're right at the edge, it's possible that if that's the case, then it doesn't matter how small your error is, you're going to die. Okay, so that's discontinuity, and that's why we want to, ahead of time, half of the time, you're going to assume that your function they're dealing with is continuous. Otherwise, this kind of behavior, it ruins all possibilities of reasonable analysis, because there is a gap between them, and like I said, if you're talking about any kind of processes, then there is a hidden instability in the formula. And like I said, so it doesn't have to be this dramatic, but it could cause errors in computations, and errors of computations could accumulate and then propagate, and then you end up with a real actual catastrophe, such as bridges falling down or stuff like that. So if you're not careful, because the accuracy that we can assure is only limited, right? So accuracy of measurements is limited, accuracy of computation is limited. So so you'd better make sure that the errors that they produce are also limited. And this is the error is unlimited. It doesn't matter how close my x is over here. Doesn't matter how close I am to y, to 0. The error is not negligible. So this is this would be the error. Okay, so so that's the problem with discontinuous functions. So that's why I'm not sure. It is certainly, in a way, it is easier to think about of what's going on around you, especially in the physical world, as if it is changing continuously rather than abruptly, incrementally, because you avoid these nasty possibilities. We cannot entirely avoid them, but at least we try to build on calculus and some basic physics on this foundation of continuity. And continuity, as you can see, that idea is based on the idea of limit. Okay, so we're going to use limits of sequences in order to study limits of functions. So this is one good example. Let me do some more of this kind. So more examples. So the functions I want to look at are cosine x. So we were following pretty much the same idea, but in a more specific way. G of x is 1 over x, and h of x is equal to sine 1 over x. Okay, so once again, these are functions. They are not sequences anymore, but we want to know about these functions is, once again, what is happening around x equals 0. What is happening around x equals 0? Does it, once again, is there a gap there or not? And so once again, the idea is try to approach 0 with a sequence. Okay, so naturally the simplest one is 1 over n. We just tried, and we see then see what's happening to y. So these are all y's, right? So each of these functions will produce a sequence of y's. Okay, so there will be then this is an, and then well, actually I call it xn. Let's call it xn, and then we have 3 sequences of y's. So a sequence of x is naturally 1 over n, and then we have an equal to cosine 1 over n, bn is equal to 1 over 1 over n. That's the easy one. And cn is equal to sine 1 over 1 over n. Okay? So you see what has happened. I simply replaced each x with 1 over n in that manner that we just discussed. So I have my sequence like this. These are xn's, and then each function produces y's, but they produce different functions. They produce in different sequences, but they're all here. So an, for example, it will be right here. So you can, if we can carried out algebraically in a very easy manner. I mean, with the experience that we have had, we shouldn't be having any trouble. So if I look at Bn, what's the... I just simplify, right? So once again, Bn come from g of x equal to 1 over x with xn replaced with 1 over n. Things are very simple. I get n, and so I can tell what the limit is. What's the limit? What? Infinity. So as n goes to infinity, n goes to infinity. Okay, so the limit of this sequence on the y-axis, so this is on the y-axis, is to infinity. So see how the behavior is kind of I'd say a bit uncomfortable. So xn behaves like this. This is how xn behaves. But look at how it's happening to y. It goes like this. Like this. Well, let me fix that. Like this. So these are y's. Once again, the blue one is x's. And here I'm talking about the function cosine x. So this is the sequence of bn's. This is sequence of xn's over here, 1 over n. It goes towards 0. In the meantime, it is nothing like what we just saw here in either case. In fact, the y-n's or bn's go to infinity. Okay? So that tells you what roughly the graph looks like, right? What does it look like, the graph of this function? Let me, maybe it's time to run another numerical example. So I'll do Excel again here. To illustrate this, we have these 3 sequences. Let's do it numerically rather than trying to do too much algebra. I think it is a good time to do some Excel. Okay, so I'll do all 3. Okay. Okay. So so these will be n's, and this will be an, bn, and cn. Okay. So n starts with 1, and then I add 1 every time, so equal to this plus 1. Okay. An is, what the an was, I forgot. Cosine n, right? 1 over n. Cosine n. Okay, equal to cosine 1 divided by n, right? Okay, close parenthesis, enter. Okay, but let me, we're doing bn, let's do bn. So it is equal to simply, it is 1 over n, equal to 1 over n. Hold on a second. 1 over n, it's kind of silly. Okay, well, 1 over n. Well, it's n. Let me plot just a function. So rather than, well, let me do this. Let me do it differently. F, G, and H. So F, G, and H. So I will be looking at just the to begin with. I will be just looking at the function. So I'll put x's here. Yeah. Okay. I think this is better. Insert. Here it is. Okay. So I will plot the functions first. Okay, and then I will try to actually see the sequences there. Okay, so I'm plotting function g. I'll put x's here. Okay, so it will be starting with 0, say. Okay, and let's add plus 0.1 equal this plus 0.1. Okay, then this is equal to 1 over, well, we got to start with 1, otherwise, okay, let me do it this way. Okay, here's how I'm going to do it. I'll start with 1, not here. I will start with 1, and I'll go backwards. We're going right to left anyway. So, and then I will be subtracting 0.1. Okay, here it is. Okay, so and this one is equal to 1 divided by this. I think it is, okay, I think I'm making it just way too small. Okay, so this is my function. So this one is, we'll deal with it later. Okay, I think I did it, mistake again. Copying, okay, like this. Okay. Maybe another 0 here. Okay. And like this. Okay, so that all there is, all we're looking at, ignore f for the time being. In fact, I'll probably erase it. So this is my function, which is 1 over n. Okay. Okay. 1 over x. Okay. The functions, the values are computed. The trend, as we are progressing very slowly from right to left, the x is going from right to left towards 0. And what's happening to 1 over x? It is growing, but kind of slow. Okay, so let's add some more. Okay, well, you can probably see, where is this? Okay, when did we get close to 0 is around 100. So so you can see, I wish these were numbers. Okay, so you can see what's going on. Well, maybe we need more decimals here. So then the x's in this column, y's in the second column, and you see what's happening. X's are decreasing, and what's happening to y's? They grow little by little until they reach a number. You look at what has happened. Excel sort of gave up here because it did not really understand this number as 0, but rather something close to 0. Why is that? It's not thinking of this 0. It looks like 0, but it's really not. How do we know it's not 0? If it was actually 0, the Excel would say you divide by 0. But it's not the case. Why? Because we carried 100 computations by subtracting 0.01, and the end result is not exactly equal to 0. Okay, which is in a way good news because it really illustrates the point. So we got close to 0. In fact, we passed 0 slightly, and by how much slightly? Look at how huge the number is. This one. This is 1 over that. Okay, and you can observe the growth of the value of the function. That is just tremendous. Because you divide by a number that is very close to 0, which gives you a very large number. So the reciprocal on the right of the number on left, it becomes very large. In this particular case, it's negative when you take the reciprocal. So so that's the idea of testing for convergence, and try to understand what the graph looks like. Let me try to. It should be no trouble to plot it. Yeah. Okay, so that's what it plots. So that point we're looking at is over there at the bottom, and it's so far off the x-axis, so the rest of the graph looks like a straight line. So all the curving has disappeared because the proportion, it's all out of proportion. Okay, so best we can do. Let me try. What happens. Okay, let me just add it. Okay, if what happens if I just delete it? Okay, so that's the real graph. That was a real graph too, but because it was out of proportion, and the Excel tries to fit the whole graph within the window, these curves became totally flat. Because that curving was it's so small in comparison to that number that it was just one horizontal line. But really, this is the graph of the function. Let me maybe stretch it a bit. so we can appreciate this part of the behavior. The what's to the right of 0 is really what we care about. This sequence does not give you all the values because that doesn't solve the problem that we're trying to solve, because it only gives you 100 points, and we want to have infinitely many points sequence reaching towards 0, and then so that's why the numerical methods here only give you a picture at best, and we have a picture and it helps us to understand what's going on, but really we cannot say anything more than that at best. It does suggest when you had that number that we just removed, it definitely tells you the scale of the mismatch between the graph that looks like actual graph and that division is so large that the graph disappears. So anyway, we'll continue with this and try to sort out those 3 examples. Okay, thank you. So we'll meet tomorrow.